Okay, so today we're going to go ahead and combine momentum conservation with some other ideas. So let's go ahead and look at this problem. So we have a 1 kilogram block on a frictionless surface attached to a 20 centimeter long spring. I'm going to go ahead and just work on my conversions right now. I'm going to know I want centimeters and meters. So that's what, 0.02 meters. That has a spring constant of 6,000 newtons per meter. A 10-gram bullet, which is what, 0.01 kilograms, is fired straight into the block where it sticks, causing the block to compress the spring a maximum of 5 centimeters, which is what, 0.05 meters. What is the speed of the bullet? Okay, cool. So we want to find that speed at the end. Awesome. So let's look at this problem. Is there a collision that occurs? Yes, there is a collision that occurs. So we're going to have to use momentum conservation if a collision occurs. When momentum is conserved, we always have to look at the instant right before and right after the collision. And I want you to keep in mind what type of collision this is. The objects stick together, so this is in an inelastic collision, what happens in an inelastic collision? Okay, we know in an inelastic collision, kinetic energy is not conserved. Okay, keep that in mind. So first what let's go ahead and do is let's go ahead and draw a before picture, and let's go ahead and draw a after picture. So we're going to again look at the instant right before the collision and right afterwards. So beforehand, we have this bullet, which has a 0.01 kilogram. We don't know the velocity of it. It runs into a 1 kilogram block that has a velocity of 0. After the collision, they are going to go ahead and stick together. So their total mass is 1.01, and velocity of both we do not know. Okay, so let's go ahead and set up our momentum equation. So we have 0.01 times v, and I should write momentum initial equals momentum final, plus 1 times 0 equals 1.01 v both. Okay, so at the very end, our goal is to find this velocity right there. So in order to find that, what do we have to find? It looks like we're going to have to find velocity both. Okay, so let's see here. How can we do that? So we want the velocity of both of them from okay, so we want to find velocity of both of them. So let's see. Afterwards, so the bullet hits it, and I'm going to start calling this now, the bullet hits it, and then what does it do? It compresses the spring a distance of what? 0.05 meters. Interesting. So now I'm going to go ahead and use this as my before and after picture. What type of strategy can we use if we want to find the velocity of both of them and it compresses something completely? Oftentimes when we're dealing with springs and velocities and things changing positions, I love energy conservation. So beforehand, let's think about it. What type of energy does it have right after the collision, which is now our before picture when we're dealing with conservation of energy? And again, previously, it's conservation of momentum. Okay, so beforehand, it has kinetic energy. Right after the collision, the spring is not compressed at all. Well, afterwards, the velocity is at rest at the very end once it compresses the spring all the way, and it has all spring potential energy. So we can use KE equals US. Cool. So whoopsie. Cool. So KE, our equation is what? 1/2 mv squared. US is what? 1/2 kx squared. So let's see. The mass is, okay, we're dealing with both of them together. So the mass needs to be 1.01. We want to find the velocity of both. That squared equals what? 1/2 k, that's our spring constant, which is what? 6,000. X is how much it's stretched or compressed. Keep in mind they give us a 20 centimeter long spring, but that's just useless. It's compressed a total of 0.05 meters squared. Cool. So I go ahead, do some good old math. I get the velocity of both of them to be 3.85 meters per second. Cool. So now what I can do is I can go ahead and plug that into my momentum equation. Awesome. So here we have right here, let's go ahead and plug that in. So we have 0.01v plus 0. Let's just erase my little sloppy work, equals 1.01 times 3.85. Cool. I can go ahead and do some good old math, and I get the velocity to be 389 meters per second. Cool. So that is the velocity of the bullet. Okay. So I want to go ahead and highlight a couple things after we've solved that problem. So again, anytime there's a collision, we're going to want to use conservation of momentum if there are no net outside forces, which there's no friction or something like that in this problem. This collision was an inelastic collision, so we know that some energy goes to like sound energy or heat energy or other things when that collision happens. So momentum conservation only works for the instant right before and right afterwards. And then we're going to have to use our conservation of energy ideas to find the velocity of both of them right after the collision. We're going to have to do this with a lot of problems this year where you're combining both momentum conservation and energy conservation, or momentum conservation and constant acceleration equations, or various things. And what I want you to think about with these problems too, does the collision occur at the beginning or end of the problem? In this case, the collision is going to occur right at the beginning. It's the first thing that happens, which is why, like I set up our conservation momentum equation first. You could also set up the conservation of momentum equation second, and then do the conservation of energy first, if like vice versa occurs. But just make sure you solidify that in your mind.